in this episode of Street Talk Unplugged.
Today, we are speaking with Dr. Thomas LUX, a research scientist at Meta in Silicon Valley. Don't forget to join our amazing Discord community. We just had our first event on Wednesday on discrete program synthesis, and we've got plenty more things lined up. As always, if you like content like this, consider hitting the like and subscribe button, and also rating our podcast on Apple Podcasts, because it really helps us out. Now, in some sense, all of supervised machine learning can be framed through the lens of geometry. All training data exists as points in a Euclidean space, and we want to predict the value of a function at all of those points. Neural networks appear to be the modus operandi these days for many domains of prediction. And in that light, we might want to ask ourselves, what makes neural networks better than classical techniques like nearest neighbour from a geometric perspective? Our guest today has done research on exactly that problem, trying to define error bounds for approximations in terms of directions, distances, and derivatives. Now, the insights from Thomas's work point at why neural networks are so good at problems which everything else fails at, like image recognition, for example. The key, according to Thomas, is their ability to ignore parts of the input space, to do nonlinear dimension reduction, and concentrate their approximation power on important parts of the function. This geometric perspective shows that many different neural network architectures are equivalent to data augmentation, yet the standard MLP, the multi-layer perceptron, still underpins everything at the back end. All of the inductive priors in neural networks are essentially data replicators to enable an interpolation regime for a particular invariance of what would have been extrapolation. Now, they do this by replicating lots of copies of data into the ambient space so that the MLPs on the end can act as a locality-sensitive hashing table. Take self-attention, for example, right? Transformers. They just permute two tuples of your set data, which is to say generating all of the possible pairs in every single layer. This, in effect, marginalizes over the domain of that particular invariance, which turns out to be very powerful in discrete token prediction problems like natural language processing. Interestingly, though, Thomas thinks that the secret is in the aggregation rather than the permutation of the values. Anyway, on that, I recommend you check out Fabian Fuchs's review article on learning on sets. Fabian has some ridiculously deep insights on how these models work and geometric deep learning in general. And guess what? We're going to be having a deep dive discussion with Fabian in the next few weeks. So I'm so excited about getting him on the show. Now, in this show, Thomas LUX explained that the main reason MLPs outperform simple space partitioning algorithms is that they work in high dimensions and that they can, or at least to some degree, disentangle data density and information density. Having lots of data sampled in a region of the function space doesn't necessarily mean that it's salient, right? That it's a salient place to learn from. In neural networks, the partitioning of the space is driven by error, and it's weighted by the number of samples, so the neural networks are not able to completely disentangle this signal. Now, neural networks also support creating a non-regular input-specific lattice to decompose the input space, which is something that other geometric methods like Delaunay triangulation that simply can't do. Now, after our episode of LeCun and Balistriero, we had a few comments saying that this spline conception of MLPs was only relevant to ReLU activation functions. Well, today, let's just say we're going to dispatch with that notion rather quickly. So, now, I give you Dr. Thomas LUX.
Okay, so we are here with Dr. Thomas LUX from Meta AI Research over in Silicon Valley. Thomas, introduce yourself.
Yeah. Hi. So yeah, you got it. I'm Thomas. I've been with Meta since April of last year. And well, largely we connected because of my hobby research, but I've got a PhD in computer science. My background's in numerical analysis technically, which is the study of how error grows as you compound computations. But I have a deep interest in AI and its roots in geometry and directions, distances, and derivatives, and trying to come up with new techniques and push towards, better artificial intelligence algorithms, more robustness, more consistent behavior, everything.
Amazing. Well, when we first met, Thomas, you sent me your paper, which was all about comparing different interpolation methods with MLPs. And it was really interesting for me because, recently we had that conversation with Randall Balistriero and we learned all about this spline theory of neural networks. And that is very much about carving the ambient space up into these polyhedrons. And all of a sudden, I guess the reason it was such an insight for me was I could suddenly think of MLPs the same way as I've thought of traditional machine learning algorithms. I've always thought of them as, in a variety of slightly different ways, kind of chopping up the input space, either by having an epsiloid around the training data or as decision trees do, kind of carving them up with these discrete rules. And now suddenly I saw neural networks in the same way. But actually, in that paper, you were very much seeing all of the machine learning algorithms in that way. So can you give us a bit of an intro into that paper and your thinking?
I originally started doing approximation style problems, which is like all of machine learning, supervised machine learning, in grad school, but only using techniques that are like strictly founded on geometry. So the most basic and obvious example is nearest neighbor. So the idea, right, is you have some input space and you have some output space you're trying to approximate. The first time I showed my neural network architecture that I'd used in my paper to my advisor, he's not into neural networks. He's only into a lot of older mathematical stuff. And he was like, oh, it's just a piecewise linear approximation. And it was funny. This is early in grad school. I was like, oh, actually, yeah, with ReLU activation, it's just a giant piecewise linear function. So as soon as I knew it was a giant piecewise linear function, in my mind, what it connected back to was the Delaunay triangulation. And Delaunay triangulation's got a lot of interesting properties. I actually worked on a code with my lab mate that we published in grad school on that. It's a great approximation technique because it's the generalization of linear interpolation to any dimension. So it's super consistent, right? It's determined. It has some properties that we can prove, which is really nice. And that was like the emphasis of my PhD, is trying to come up with these provable properties of, error bounds. How do you stop your approximation from getting worse? Then I, now with Delaunay and the neural network both being piecewise linear interpolants, I was like, okay, so that's my connection, is like, everything a neural network does, its goal is to break up the space into little, well, in this case, it's polytopes, because it's not always simplices like a Delaunay triangulation uses, but yeah, and fit those shapes to whatever your underlying surface is.
Amazing. I mean, for our audience, could you introduce some of these concepts? So we spoke of simplices and de Launay triangulation and Voronoi as well. So, these are all ways of, kind of partitioning a Euclidean space, but could you give a bit of flavor on that?
Yeah. So let's see. The best place to start, I think, is with pictures, because everything's intuitive when you can draw pictures of it. And even when I'm trying to understand neural networks and stuff, I go in and draw pictures of it. And I have some visuals of like the actual regions that a neural network breaks a simple function up into so you can see it. But the premise of a Delaunay triangulation is like, start with a 1D picture and, draw lines between points, and that's your interpolant. That's the function you're going to guess if you just have a 1D function. Now, once you go to 2 dimensions, how do you draw the lines between the points? Because it's no longer obvious which direction to draw the line. And so it turns out, if you make the only required property, that if you, there in 2 dimensions, exactly 3 points define a circle, right? So if you look at the circle that intercepts any set of 3 points, you could call it a nearby, like a nice simplex, if the 3 points that hit the edges of that circle are the only points that touch that circle, and no others are inside of it. And there's actually a really good visual that's just on the Wikipedia page for Delaunay that I'm sure you can show here. But it's that single property results in this these collections of points. And so it's always going to be, if you have d dimensions in your input, it's always going to be d plus 1 points. And that will form the generalization of a triangle. And that is what defines a plane. So if you think about it, a linear function in any dimension is defined exactly by d plus 1 points. And so when you break up all of your data, you take your input space and you group them in this way where what they call that is the circumball is empty. The ball that intercepts the points of the vertices of a simplex only has those points on it. Then you form a unique piecewise linear interpolant of your data. And unique is really good, right? Because when we want to prove things, you need to say with confidence that this is the only outcome. And once you have a Delaunay mesh, you can start to actually prove properties of the error, which is what led me down that whole paper track that you read.
Fascinating. So just to reiterate again, because I really want to articulate this as clearly as possible. The magic of machine learning is that we have a bunch of training data in Euclidean space, and via a variety of techniques, we can create some kind of enclosure. And then inside that enclosure, we can interpolate, and that forms some kind of approximation bound, for us to generalize to new test data. Now, of course, we'll get onto the curse of dimensionality in a minute.
Yeah.
But the basis of your paper was you experimented with a whole bunch of these highly principled ways of partitioning the input space around the training examples and performing interpolation within those, let's call them polytopes, but maybe that's not the right. And they compared rather favorably to MLPs.
Yeah, so that was what I think was of most interest to my advisor. And a lot of times that's how grad school goes. And also of interest to me is everything in machine learning, like you're saying, you could think of it as partitioning space, or really, I like to always break it back down to just, you've got a one-dimensional function and you're drawing a line through it, right? You're interpolating your data or you're regressing your data. You're doing one or the other. And all of this is just, how can we generalize that exact same concept into more data, higher dimensions, more data points? So the interesting result for my advisor was, these are the methods that he'd worked on his whole career. So he liked seeing them compared with what's really common right now, which is the neural networks. But also, if we prove something is the case, like we prove that Delaunay is good, then we want to see it. We want to see those results in action. We know that Delaunay converges on the true underlying function as long as it's deterministic, or it's not stochastic. It has exact values. And so the idea is, all these problems that we're solving in machine learning, presumably if we're getting good accuracy, we're converging on the underlying function. So Delaunay should perform well. And that was the motivation for the whole paper, is we lay down Delaunay, linear shepherd. So shepherd and variance are just inverse distance weighting functions. So like, imagine nearest neighbor, but instead of doing just the nearest point, you do a weighted combination of all your data, and you determine the weights with the distance to the data point. Compared all of these with some like regression techniques from the 90s that are good, like multivariate adaptive regression splines, which is also a very neat space partitioning algorithm. And what it came out was, sure enough, these other techniques also work really well. It's not just neural networks that work really well, but neural networks do excel in a case that is very challenging for all the classical techniques, and that's when you have high dimension, and when the surface you're trying to approximate, so if you think about your data, it lives on some manifold somewhere in your input space. When that surface is a nonlinear subsurface, so like you can't just take the principal components and get your function. What if the function is really important in this part of the space and really important in this part of the space, but then everything in between isn't important? The neural networks, the magic that they have that nothing else has, is being able to do nonlinear dimension reduction. So they can reduce the dimension of your whole input space and simultaneously capture the fact that there are disparate sets in the space that are important.
I don't think it's necessary to bring in nonlinearity at this point. Like, we're just talking about piecewise linearity, right? And so I think the point here is that, I'm assuming, but you tell me, when you lay down a Delaunay triangle, let's just pretend it's a 2D plane. Mm-hmm. Okay, I'm just trying to interpolate a two-dimensional function. I'm assuming you just laid down some regular Delaunay triangulation, like the equivalent of just a typical triangular mesh or something, right? Because the hard part is choosing the points of the triangles. It doesn't have to be a regular mesh. I could have a big triangle over here, a bunch of small ones over there. And unless you've, come up with something like you just said, the thing that neural networks can do, which no other method up until at least max affine splines, which, we had this review this paper recently, can do, is they can divide up that space adaptively. They can decide, look, I need lots more triangles over in this region. I don't need a bunch of triangles over here. There's nothing here beyond just piecewise linearity. It's just, it can choose to refine regions of the space adaptively. So that's what we're talking about, right?
But so I think, like, if we think about it, every time we want to talk about how good something is, we need to make assumptions about the input. And so if you have this 2D plane that we've drawn, right, and you've got a lot of points in one place and not a lot of points in another place, where you have high density of data isn't necessarily where the underlying function is changing the most. So if you want to talk about, if you're thinking about just drawing a piecewise linear interpolant over a surface, what you do is you want data where the function surface changes the most, because that way every time the function changes, a linear interpolate gets worse, right?
Well, no, that's really, I want to put an anchor down on that.
Yeah,
So
yeah.
you're saying where there's loads of density of data, that might not be, a region of information. Do neural networks, for example, do they suffer from that? So if you give them lots of data in a region of the ambient space, will they place? Because I want to frame this up a little bit, because I think where we're getting to here is neural networks are parameterized models. And what they do essentially is they place all of these basis functions in the ambient space. And where those functions are placed is of interest to us. So let's start with the assumption that, do they get placed more densely where there's more data density rather than information density?
So that is the beauty of following the gradient. They place basis functions where error is high. That's where the basis functions will cluster to where the error is high. If you have a lot of data in one region and no change, perfectly linear flat function, as soon as one basis function hits that data, the gradient goes to 0. So the neural network goes, oh, well, I don't need more information there. So it does do a good job of adaptively saying, I only need information where the underlying function is changing a lot. And this is where classical techniques and neural networks diverge. And I'm working on this theory. I want to have a good, robust theory for neural networks. But where they diverge is the classical techniques largely assume your input space is nice. So your data is spaced according to the function. They assume that directions are all equally important. And that's not the case. When we're doing image classification, not all directions are equally important in pixel space. Pixel space is a very weird phenomenon. And we don't really have any theory that covers the idea of this. I call it like a sampled subsurface functions. So if you think about image recognition, it's not the function that you're defining isn't in a million dimensions, right? We live in a three-dimensional reality with time, fourth dimension. So where are we getting a million dimensions from? Million dimensions are exponentially larger than 3. And it's because we have this sampling phenomenon, right? We sample our single underlying function in lots of places. Where in approximation theory do we have error bounds for functions that approximate this sampling phenomenon? And that's kind of the direction I'm trying to go with my personal research. This is not affiliated with Meta, but it's something I'm very interested in. And it's and this is the thing that neural networks are really good at. And this is that was like my primary takeaway from doing that deep dive comparison between classical techniques and neural networks.
Fascinating. So when we spoke last time, Thomas, you were saying that you discovered something really interesting around the placement of these basis functions in the ambient space. It always occurred to me, my intuition was, and I think I said this on the LaCoon show, and I realized I was wrong after speaking with you, is that I assumed that the basis functions would be placed in the vicinity of the training data. But that's not the case, is it? You've got some preliminary research that they're randomly initialized, of course, and they don't really move very much. The only thing that changes is their pose.
Yeah. So, and this is this is the great question. And all through grad school, before I was more invested into research for neural networks, I was solving a non-convex optimization problem over your data to do regression when you have all this other stuff. That seems silly. Why are people using neural networks to do all these problems when think about the wasted resources of resolving a regression problem from scratch when, with classical techniques, you have immediately updated models every time you have new data. You have a lot of benefits that come from that. What I realized though, initialization matters, but we don't have good deterministic answers for what initialization is good, when, and why. And so, the first question you might ask is during training, if you're trying to prove something, what about my network or model architecture can totally prevent me from converging? Or actually, what even just does happen? And so I went in and I recorded, how do all the shift terms change for all the linear basis functions? How do their directions change? How do their magnitudes change? And what I found was really interesting. If you look at this, the shift terms, for the most part, don't move at all. And what that tells you is in this giant non-convex optimization space that we're solving for a neural network, a lot of learning can be done with directions, but a lot of weight is coming from this arbitrary initial choice of shift terms. And why is that? And certainly there's some great theory that's underneath this that we could dig into. And that's kind of that was my motivating initial experiment, is seeing what does and doesn't move. And now after, I don't know if you've seen the paper that's blown up recently about forward gradient or forward differentiation and not needing the full back propagation for the gradient. So this has been all over Twitter as of like Friday. And it's interesting.
Can you fill us in on that? And also, I'm really keen to know your theory on, as you said, let's say you've got poses and shifts. Is it because one seems to dominate the other in the optimization objective? So is it just a symptom of we haven't tuned this thing correctly, or do you think it's more fundamental than that?
The real thing is it's a hard problem to solve. It's not an easy, like we've created a difficult optimization problem. And when your space grows, right, and you're trying to optimize any function, just classic optimization, if it's not a convex function, so you can't guarantee that downhill gets you to the global solution, there's no other answer than to search everywhere. There's no magic. There's no way to say, oh, I actually know I need to go this different direction. The only thing you can do is follow the gradient. You can make some guesses. So what that tells us is we need more. We need a little bit more information. We need to look at the way the neural networks are structured and see if we can glean a little bit more than just, oh, it's a non-convex space.
Well, if I can maybe more directly, answer your question, Tim. I mean, it could be something as simple as the fact that if you change the direction of a hyperplane, that's going to impact every single thing that you've calculated for all data points that are on the side of that hyperplane. Whereas if you shift its position a little bit, you're only gonna chop off some data points or some other ones, but you're not going to have as much of a directional effect. It's just like the further away, if you've got an arm and you're rotating it on a circle, the further away the radius is from that point, right? You're going to have a massive change in the value.
What you're getting at is curvature. Is the loss function has a lot higher curvature with twist, right? Because if you have a point that's really far away out on the end of the arm of the basis function, and you turn it, you move that point a lot, which changes everything about it downstream. Whereas when you shift, you move all points the same amount, which is lower curvature.
Just to throw another curveball into the mix as well. So neural networks have this really interesting property of entanglement. So all of these basis functions, they are kind of like a combination of all of the topologically addressable neurons.
A honeycomb of honeycombs.
Yeah. So this optimization problem, it's not just the individual neuron, it's actually all of the addressable neurons. So doesn't that make it even more complex?
Well, yeah, and I think I always like to go back to the simplest visual I can make. The simplest answer is linear regression. When you have linear regression, your answer isn't just a function of the weight on one of your inputs. The optimal solution is a function of all of the weights on all of the other inputs. And so actually there's a conditional dependence on one direction being picked and another direction being picked, because it might be the case, like the simple explanations, there might be a case where if you only have one option, you would pick one input number one. If you had two options though, you would pick inputs 2 and 3, not 1, because 2 and 3 recreate 1. So like there's this conditional dependence that gets created once you have more options, once you have more neurons, more dimensions. So yeah, that makes it a hard problem.
Fascinating. For me, extrapolation is about this notion of continuing the pattern. So imagine we had a spiral manifold and I want to be able to predict inside the spiral manifold outside of the training range. That's what I mean by
that's a fun data set, because that always breaks those methods.
It's beautiful, right? But if I was doing symbolic regression, I would absolutely be able to do that. And I think when people talk about extrapolation, that's what they mean. So when we talk with symbolists and they talk about being able to perform abstract extrapolation, what they mean is being able to use a little bit of knowledge and semantics and kind of cast it into a completely different situation. Now, we know based on the conversation that we've just been having that the basis of machine learning models are interpolative. We're just kind of moving around in these little kind of enclosures in the Euclidean space. So I have this very loose intuition, I'd love to test it on you, Thomas, that the way that we make these models extrapolate, with these inductive priors, is almost by kind of replicating the information into lots of different areas of the ambient space so that these interpolative methods work. Now, remember, Francois Cholet said we've got to make the methods interpolative. Well, let's test the principle for a CNN. So a CNN has this translational weight sharing, and you have the tennis ball, and you're now shining the filter over the input space, and you're producing a response map. So what that's essentially doing is it's making copies of that pattern and kind of scattering it over the ambient space. Well, it's not the ambient space, it's the response map space. And then I'm doing an MLP on the end. And that's how I'm kind of extrapolating by cheating. So yes, it's outside of the distribution of the original data, but I've kind of cheated by projecting it using this CNN.
Well, and I don't know that I'd call it cheating, because almost in line with what I think it was Francis Delay said is you want to interpolate. I mean, but
I think the cheating part is that the convolution part of CNNs is not machine learned. A human being encodes the convolution,
yes.
Right? And so that's what we mean by cheating, is that a human being structuring in these.
So this is a deep area of interest for me because I'm trying to come up with any theory, and what bothers me the most is transformers. Like transformers, they're solving this problem. What are they doing that's so well? And right now, my best guess is actually there is still a much simpler architecture that might work. It's not totally. I haven't formalized it perfectly yet. But it comes down to solving this problem of apositional inputs that the ordering doesn't matter, or how many of them you have doesn't really matter. Because and this is the same for the image, for vision, right? You're sampling an underlying surface. If I yank out a few of the pixels, it shouldn't matter. It shouldn't change anything. It's really the sum of all the samples in the image. So the sum doesn't have ordering. And so I think that's what really transformers are getting at, is the ability to process apositional functions or inputs that are coming from functions that don't have an implicit ordering. And if you remove the implicit ordering, you can get back to interpolation. You don't have to worry about extrapolation.
That's fascinating. I'd love to meditate on this a little bit longer. So there are different ways of understanding transformers, as I've heard articulated by many of my friends. And I think one way, which is similar to what you're saying, is that they're a kind of generalization of deep sets, but they're permutation invariant. So like one way of visualizing how they work is thinking of them as a graph learning algorithm, where you're just learning relationships between all of the tokens. Another way I've heard of explaining them is thinking of them as an information retrieval system with the keys and the queries. I mean, do you have a really simple kind of intuition around how you think they work?
So I do want to clarify one thing. ReLU activation, weight matrices, linear functions. This is still a piecewise linear function. All we've done is we've done some feature engineering inside of it, and we've structured our piecewise linear function to match our assumed structure of the data, which is that the people what they're capturing with transformers is attention, right? Attention is combinations of things matter. Combinations matter more than order. Combinations can come in weird ways, like sometimes the patterns you want to pick up are based on combinations of elements, values at specific positions. That's all. Again, we've engineered that feature, just like Keith was saying, right? We've human learned that this architecture works well. And so the way I think of transformers is I think the most important part of them is the fact that they have an apositional operator, an out of order operator. It doesn't matter what order things go in, it creates an approximation. And why is that relevant? Because a lot of our problems are like that. People will still understand sentences if you rearrange the words. They'll still recognize words if you rearrange the letters. It is the context of what is there at the same time that matters more than the specific order that it's in.
Yeah, but let's be really careful, because if I say Bill kicked John and I swap the positions of
Yes,
Bill and John, I wind up with the opposite conclusion. So I think we're taking this a bit too far. Like even in images, you said order doesn't matter. That's obviously wrong, right? Like the 2D spatial representation or spatial relations between the data, matter a lot. I agree you can take out some pixels, but that's because you have the idea that there's a world model which says underneath that is some larger scale feature, and I'm doing some kind of like subsampling of it. So I think it's just that transformers add in the capability to ignore order. Like a lot of what, Tim, a lot of what we've kind of discovered in the past here is that these invariants that people encode, one way in which, they try to do them if they can't figure out how to actually encode it in the structure of a neural network is through data augmentation. And when you go to do data augmentation, what you do is you do tons and tons of transforms to your data. You do all the transforms that you want the neural network to learn to ignore. So for example, if you want to learn to ignore order, you put in all the inputs in every conceivable order. If you want to learn to ignore rotation, to learn rotational invariance, you rotate all your images by increments of 5 degrees. So interestingly enough, what I was going to say is that a lot of the invariant structure is about teaching, or a lot of what we're trying to get neural networks to learn how to do is to ignore certain aspects of the data. And from my perspective, that's exactly analogous or even equivalent to abstraction. Abstraction is all about ignoring elements of the data.
That's right, but it's also, I think, testing the principle analogous to marginalization in Bayesian models. So what you're doing in a CNN is you're basically saying, I'm going to go over the entire domain of this thing by shining it everywhere so that you can learn it in all places. In a transformer, it's learning k tuples, right? So you've got permutation invariance for sets of two, right? So all of the combinations. So what you're doing in that quadratic transformer layer is you're saying, okay, well, I'm going to try all of the combinations. It seems computationally exhaustive to do that.
Well, so, finding the global optimum is computationally exhaustive all the time. And so what we're doing is these differentiable tricks. So whatever, if a transformer is trying to learn these possible permutations, it's only doing so by way of some differentiable kind of trick, right? Like, it's all about trying to find ways in which to have a smooth, learnable function that approximates some kind of more discrete, sort of symbolic thing. Like the point that Thomas brought up earlier about, I should be able to take an image and throw out pixels. It's not that I'm, in a technical sense, the ordering, hasn't changed, right? Because you still have like whatever pixel was to the left of one is still to the left of one, but the sequencing changed. There's no longer like stuff in between them. And it should be able to learn that. And that's about trying to learn these longer range connections that ignore, some stuff in between. And so could you come up with a smooth differentiable way to say, for example, toss out every third pixel? Sure, you could actually do that by weighting every third pixel by some alpha and then explore what happens when it goes to 0, right? And then you might be able to, and you could imagine doing that for kind of every sort of frequency and maybe come up with some cool basis functions that can smoothly transition between ignoring combinations of pixels.
My pet peeve with with data augmentation is that if we're really going to progress towards AI, then the internal functions created inside the model for whatever problems are solved. Like my analogy is, I'm a person. If I think something enough times, it almost becomes like a little program, and that a part of my brain becomes designated at auto-completing that program. And so I can create programs. If we want a model to be able,
you can synthesize programs. Program synthesis, Tim.
So if we're going to have a model that can do that, we can't have this prerequisite that we know the structure of the function we're approximating and that we can handcraft architecture.
Totally
and so
agree.
I think you're right. Like the problem is there's a mixture of positional and apositional information in these functions. And so if we're going to have one general architecture that approximates things that we don't have to handcraft, I feel like it's going to be exactly that. It's going to have an apositional front end that aggregates things and encodes them in some embedded space. And then it's going to have an MLP on the back. And the MLP does all your positional processing. And I think we'll get there.
Well, just a small quibble there. Like I'm always leery when I hear about assuming a front end, or because that's assuming a kind of implicit order, like that I do, apositional first and then positional. I think in some distant future, we're going to figure out some way to like smoothly hybridize, those approaches, and even have multi-layer kind of cyclic evaluation of that.
I try to simplify as much as possible. And the problem is you can't.
No, I hear you.
You can't put the positional first, because if you have an apositional information, you have to do data augmentation, right? You have to do all the rotating in order to make the positional function learn correctly. If you put the apositional model first, then as long as the embedding that it's producing is big enough, it could perfectly reproduce your input data, which means you keep all your information for the positional model. So actually, I think it has to be in that order. You have to do apositional first, then you do positional. And that should be, and I know I'm using these phrases weird. I mean, like, unordered set processing first, and then regular MLP, which is each input component has a specific meaning, second.
So Thomas, do you agree though with this idea that, because I'm fascinated by discrete program induction, by the way, and the potential for for what we can represent with discrete programs going forwards. But my intuition is that all continuous machine learning, it all happens in this Euclidean space. And the only way we can achieve the parlor trick of extrapolation is by littering the Euclidean space with what I see as space junk. So, we've got loads of junk floating around the Earth at the moment. All of these inductive priors, what they seem to be doing is just taking loads of data augmentation. It's all the same thing. It's creating loads and loads of space junk so that we can have the parlor trick of extrapolation and generalization. I mean, do you agree with that premise?
Yeah. I mean, I don't know if I call it a parlor trick. Like, again, like littering the space like that is actually turning our extrapolation problem into an interpolation problem. And so let's be clear. If you want to extrapolate, you have to know something about your function. Like you have to know some underlying structure to do human level symbolic extrapolation. We make the assumption that we have the correct symbolic representation, and then we extrapolate that. But that's an assumption.
Well, that's a really interesting way. That's a better way to frame it. I should have framed it like that. So for continuous machine learning models to work, we have to, Chalet said it as well, we have to represent extrapolation as interpolation, which means we need to transform it into an interpolative space. Why not just come up with an extrapolative model in the first place?
So I think it's like I always take it back to the simple example. Say I have a picture, and I give you 2 points, and you draw a line between them. You say, okay, cool. And I ask you what happens outside of that. How do you have any way of guessing?
Well, without any domain knowledge,
you have no way of guessing. So that's extrapolation is hard. If we have 2 points, I can draw a line between them, and I can say, actually, that's probably a pretty good guess. If it's a continuous function, yada, yada. If we go out, I don't know. I don't have any guarantees anymore. I mean, I'd probably just extend that line, but that's all I can guess. That's all I can give you.
But if this is the representational substrate for the kind of information we have in these models, do you think it's a good substrate for, like a lot of Go5 people talk about ontological information and discrete ways of representing knowledge and so on. Do you think that it's appropriate to store that kind of information in a vector space?
Okay. I don't often refer to the brain because I feel like usually people start referring to the brain in biology and evolution when they don't understand the problem, which is okay because we use analogies to understand things. But this is a case where I think referring to the brain is good. We know that a discrete logic space, like a symbolic logic space, and the functions you can represent there is going to be a subset of what you can represent with a continuous space. The real number line is uncountably infinite. The integer number line is countably infinite. It's smaller. But we still use language. We still use words. We still collapse to these categorical symbols and representations. And I think this is the thing that everyone's trying to capture. I don't think that's an accident. I feel like it happened because it was the most likely outcome, because it was the easiest thing to do to achieve the goals that brought us here today. And so I think there is an important collapse to categories, but I think you do it in your real space. You're still living in a real space, but sometimes it's just convenient for information storage, for compression. And then when it comes to language, for communication, like how do we communicate thoughts? Every one of us has a different thought embedding for a specific thing. We have no way of sharing that embedding from inside our neurons to someone else's brain. So we had to come up with these categories that we agreed roughly represent the same thought embeddings inside each other's heads.
Just because let's say some waveform, some function, whatever, is actually smooth, doesn't mean that it isn't so curved in certain parts of it that any practical utility of that curvature is just not relevant. So for example, in the case of neurons in your brain, yes, if you stuck an electrode on the axon of a neuron and measured it, you would find, at least all the way down to the degree of an electron volt, or however much energy is in a single electron, that it's the smooth, and continuous function. Although it's going to be highly, highly, highly peaked, right? It's going to have this pulse, okay? And so the problem is that in the sort of smooth, let's say, computer forms of neural networks that we have today, like differentiable Turing machines and neural Turing machines and things like that, the more and more they become more discrete, the more and more in which they become, kind of peaked with the very high curvature sorts of functions, the less and less they're trainable, right? So it almost doesn't matter, whether you're talking about the extreme of a discrete function, or a nice, smooth, slowly changing smooth function, if you become more and more like the other, you inherit all the pros and all the cons of whichever extreme, whichever pole you're kind of approaching there. So I think it's a bit of a like an attempt to escape the fact that it doesn't matter if you still maintain continuous functions, but yet you make them so curved that they function as if they were discrete functions. You're not going to evade the problems that we already have just in the kind of simpler, more abstract discrete world.
I guess maybe this is a good connection. Like, I don't see a reason that ReLU, like just the rectified linear or any piecewise linear, you could have picked anything. ReLU just empirically looks like it has the most promise, so let's build theory around that. You can get everywhere with that. I think introducing other functions is just, it's more complexity, and it might work for some problems. It's not going to work for others. I think generally we start with Occam's razors. Yeah.
Yeah, I agree with you there. And more profound for me after this talk with Balestriero and LeCun is that I used to, in my mind, think, because I started off with neural networks like old school when they were sigmoids. And so they were nice and smooth. And in my imagination, I always thought that neural networks were taking huge advantage of that little smooth elbow to do cool things. Like if there was a parabola, it's going to put a smooth elbow like right on the top of the parabola to match that, curvature or whatnot. And we've been asked this multiple times in the YouTube comments, but it's like, lol, if you just use a smooth function, it destroys your argument. They're totally missing the point, which is those little smooth parts of the activation functions, I think in the current paradigm of neural networks are basically just thrown out. They're ignored. It's not even using that smooth section to any significant degree. What it's doing is exactly what it does with ReLUs, which is chop up the space into this honeycomb of honeycombs and effectively take advantage of the linear parts of the activation functions to do these linear interpolations, which is why all these piecewise linear techniques continue to dominate, become even more dominant. People find when they increase linearity by putting in linearizing constraints and things like that, they get even better performance. It's all because the smooth curvature gets in the way, actually.
The mathematically principled way to say that is, I think, is you're looking at the conditioning of your function. And the conditioning is essentially going to be a function of the difference between the steepest and the least steep part, kind of in part. That sounds bad for a ReLU, but really what it means is when you apply a ReLU and it hits the linear part, this is the vanishing gradient problem, right? You make your learning problem harder if your basis functions have high curvature. Curvature is any non-zero second derivative. Yeah. If they have any non-zero second derivative, you're increasing curvature, and that curvature is going to be magnified and multiplied into the loss landscape, which means you're going to have an even harder non-convex optimization problem to solve. So if they're all going to get you to the same place in the end, I would pick the one that's an easier optimization problem to solve, which is a function that's conditioned really nicely because what's the easy way to say this is, imagine when you have a linear function and you point it a little differently, the whole space shifts linearly, right? Everything is linearly moved. Now, when you have a nonlinear function and you point it a little bit, the whole space shifts nonlinearly. And that means that all your loss function has shifted nonlinearly. Yeah.
Right. Is that why, I remember, was it Andrei Karpathy, or when ReLUs first came out, it was kind of conventional wisdom that your model would converge about 6 times faster? And is that your intuition?
Yeah. Like, so really anything we do to train a neural network faster comes down to how did we make the loss landscape nicer? That's one way to view it. We either made the loss landscape nicer, so more convex or more of the loss landscape points to a single global minimum, or we have a better estimate of the function. So it's like Adam versus SGD. Adam is almost a second order method, right? It's creating an approximation for the curvature of your function. And so this all comes back to really basic examples, right? If you have a quadratic function, a perfect one, and you minimize it, then having a quadratic approximation will get you there fastest, And so it's like the nicer we can make the function and the nicer we can make our approximation, those are the only 2 ways we accelerate convergence everywhere for all problems. Otherwise, it's heuristics. Otherwise, we've done something for a specific problem that works there, but it won't work anywhere else.
Obviously, leaving aside a couple small technicalities here, which is that sure, if you have an activation function that's using some expensive transcendental, function calls, and you're not accounting for that. So in other words, if the training time isn't in terms of sort of numbers of evaluations of the function versus how many CPU cycles, then you can kind of get into issues and mislead yourself. And let us not confuse our listeners. ReLU is a nonlinear function. It is a piecewise linear function, however, and it's important to understand that, it is, what's funny is, like you were kind of saying, the more curvature you have, the harder the optimization problem gets, unless you have a point of infinite curvature. And then it's okay because we develop, algorithms to deal with that. So like in the case of ReLU, it's got this nice linear piece where it can do all kinds of cool stuff. And it just so happens that if the data is on the other side of the function, i.e. the flat side, it just ignores it. I mean, it's, it just takes it out of the, that particular branch, if you will, of the optimization. But the problem is when you evade that by having a little bit of smooth nonlinearity there that can spread out, then it makes your optimization problem harder.
Very cool. Well, Thomas, what's top of mind for you at the moment?
My personal track is trying to, figure out anything that I can prove, right? What can I prove about a neural network? How can we get to a place where these are more deterministically and consistently trainable, where they can solve the same network, same architecture can solve more problems and solve them with bounds. People care a lot about explainability. So when you can prove things, you can usually explain them a little better. And right now my track it's kind of an interesting one. And it relates to what I mentioned earlier, which is this, people are seeing, I think it's the forward derivative. They're saying that you don't need to use backprop to train your network. You can train your network without backpropagation. You only have to do it layer-wise. You can do it faster. And this actually closely relates to the line of research that I'm most interested in right now, which is initialize your network, right? Whatever network you want. Push your data through it. Record the representations of the data, your embeddings at every single node in your network. There are a few properties there should be things that hold true. If you look at the very input of the data, when you reduce it, right, when you push it through the network, its principal components are going to change. So that means if it only has 1 or 2 dimensions of variance, that will change to the network. We would hope it actually increases, but never fatally decreases, right? If the principal components go to 0, you've squashed your data, you have nothing. So that's one property. The other is somehow your data should morph to look more like your output as it goes through the network. So at the very last layer, the similarity between your representations and your final output should be very high. And one way of thinking about that is your neural network, you can think of the whole thing up to the last layer as a learned basis approximator, which is it's trying to learn a set of basis functions such that at your last layer, you have a set of good basis functions over your data for representing your final output. And so if we look at this in this context where we're trying to construct good basis functions at the output, then we can construct error bounds on those basis functions. And if we care about the principal components on the input, we can track how the data changes through the network. Then we can probably prove some properties about convergence. And I've got some really promising initial groundwork, but nothing to share yet.
That's fascinating.
Cool.
I mean, just 2 things to pick up on there. Just because, again, our intuition before was that neural networks are transforming the data, but they're not, are they? They're just transforming the basis functions, which give the appearance of transforming the data. Let's say if you were in the context of a generative model. Okay, that was the first thing. The second thing is you were talking, you glazed over it a little bit, and I'm not familiar with this new model that doesn't do the backprop, the forward growth.
Yeah, I saw a lot of conversation around it on Twitter. People are excited because it's faster, right? You don't have to do backprop all the way through the network. And I read through exactly how they compute this gradient. That was what I was really interested in. Like, wait, that doesn't make sense. How can you have information about the function you're approximating travel all the way through the network if you're not doing backprop? Like, if there's no computational connection between your output and the first layer, what's happening? And if you go and look, and some people can run this experiment, it's fun, and I've done it, it looks like it's true. Look at the principal components of your data in those embeddings. At your first layer, let's say you're doing a smaller problem, you've got mostly 5 components. And the next layer, let's say you've got 30 or 40 internal nodes in your MLP. Maybe it'll have a little bit more than 5, right? You would think because the nonlinear basis functions can increase the variance of your data. So maybe it'll have 6 major principal components. And you would hope by the time you get to the last layer, you have 30. unique principal components of data, right? You've increased the variance of your functions. If you look at initialization, that's not the case at all. It collapses to 1 almost always. If you look at the principal component distribution of your data, it collapses fast.
Wow.
And what that means is at initialization time, we're losing most of the data. And when you train with that method that paper's saying, look at the principal components of your data after you've trained with that method, it's increased. The variance is high. It has no connection to your output, but just solely by increasing the diversity of basis functions that you're approximating over your space, you get a better final result, right? I could just do a linear regressor over the final embedding of that model and get a better result than I do with a regularly initialized network. So it's more of an initialization scheme than it is an actual training paradigm.
That's absolutely fascinating. We'd love to have another conversation with you. Thanks for coming on so much, Dr. Thomas Lux. It's been an absolute pleasure.
Thank you.